This is that little 10 megahertz frequency reference. I leave it on continuously. It's been running ever since the last video. And if you remember, this reference contains a 10 megahertz RF source. It's a temperature controlled enclosure with a high quality crystal in it. And this would probably have been enough to supply an output signal. But I wanted to intersperse a buffer amplifier between the output of this oscillator and here. The amplifier I chose was a 2N5109 amplifier. It was actually a kit. The kit was provided by SV1 AFN. That's a blackboard here. It was rather expensive, between $40 and $50. But it's not designed for this application. It's designed to be a receive amplifier with the input at minus 50 dB or something. I do have a attenuator, in fact. So I ordered from AliExpress what I think might be a more suitable amplifier. I've started getting a lot more stuff from Ali, or at least I've started ordering a lot more stuff. But you have to plan 2 months ahead. AliExpress is extremely long delivery here to the United States. There appears to be 3 ICs. I'm going to hazard a guess that this is a 3-terminal regulator. This is a VCC in. I think the voltage applied to the 2 devices will be somewhat less than 12. And then we apparently have 2 stages of gain. It's advertised as a 2 watt. That would be 33 decibels output. Now, I don't intend to build a transmitter. I'll operate this at a really low level. But I think this can take input of 1 milliwatt, which is more or less equal to the output of the crystal oscillator. I can't read the markings, but I'll look at them under a microscope, and if I can find out what they are, they'll be in the description below. These are actually sheet metal screws. That's a shame. I had hoped they used machine screws. There's no provisions for mounting this thing. What I thought I would do, and I may still be, if I can take these out and get threads, I'll replace these little screws with standoffs. And that will also give me a chance to see that there's heatsink compound applied between here and the sink itself. It appears to be 3/4 of an inch between the top of the fins and the unused ground terminals on this SMA connector. And then it's 2 inches square. This amplifier costs $12 delivered, $8 purchase cost, and $4.50 shipping. Now I'll be operating this at 10 megahertz. The paper says the usable frequency is 1 to 930 megahertz. Current 3 to 400 milliamps. And then this is some Chinglish. I believe I'll have to put a load on the output. I'll probably just use a pad or an attenuator. And then not more than 12 volts. More than 12 volts would only cause overheating of this 3-terminal regulator. I've gone ahead and tapped these M3. I did run a 2.5 millimeter drill through here. I don't think I would have had to. It was, if it removed any metal, I didn't see it. So these screw in nicely. Take the screw out. Yep, that works well. The through holes, which are meant to carry heat, are all located around this second stage device tab, which is where the heat is supposed to be carried away from the device. Now that's a lot of heat shrink paste. I'm using this HY 510. So it's going to squash out. So what I'll do is try to squash it downward. You can see that some of the paste is actually squeezed through the vias. Now, I've purchased a number of different heat sinks through the years with Chinese mounted circuit boards fastened to them, and I've never encountered conductive heat paste. So if you can do so without damaging whatever it has, you can remove the screws, take it off, and at least insert some paste in the affected areas. I would not use hardening compound. I prefer a compound that remains fluid, or at least I can just take it apart without straining anything. And while the physical size of these two amplifiers is almost identical, the drilling pattern, of course, is not. What needs to be done is to shift these holes slightly and remove these two standoffs. So you project up from the bottom. Well, now I'm going to have components that interfere with those standoffs. I've got the new amplifier loose, but it's powered up off the buck power supply. This is now a 40 dB attenuator. Eventually this signal goes through this T and ends up in the input of the amplifier. The output of the amplifier goes through another T onto a 20 dB attenuator and then a 52 ohm resistive cap. The oscilloscope, channel 1, which is yellow on my oscilloscope display, and channel 2 taps off here, and it's the purple or violet display. Looking at the scope, you can see a sine wave output from the attenuator. and a sine wave output from the amplifier. Essentially, these are the input and output signals from the buffer amplifier. Now the whole shebang draws 760 milliamps. The input, of course, it's after the attenuator right here, reads 180, 175 millivolts. The output reads 8.5 volts, both peak to peak. So 175, 180 in, and 8.5 out, peak to peak. Both are very nice sine waves. This is generating some heat. I mean, it doesn't hurt to lay my hand on it, but I don't know if I would keep my hand. Well, no, it's not hot at all. Neither the inductor or the switching chip isn't making any heat in the boost converter. So I think now that I know what the configuration is going to look like, I'll mount this in the case. I've gotten it all done in the case. The only thing left is to put the lid on. Again, this is a 40 dB attenuator. Down here, underneath the blue LED, is a 3 dB attenuator. The amplifier cautions to always have some load on it. Well, this attenuator, in addition to cutting the output power in half, causes some load to be applied. Not necessarily 50 ohms, but take out my oscilloscope deck. My intention is to let it run with the lid on. I'm worried about heat buildup inside this case. So I'll revisit the whole thing after it has a chance to, I hope, not burn in.